After covering the theory of T/Z tests in our previous lectures, we're going to move on to doing the t-tests using tools. I'm going to take you through SAS, SPSS, Statistica, and demonstrate how do we perform a single sample t-test in all the three tools. The first method that we're going to use is going to be the critical value method. I'll explain the term critical value, what does it imply in this context. Right? So let's have a look at our first exercise. It says that on the HSB2 dataset, test the following: whether average score is 55 for all scores or not. Now on the HSB2 dataset, if I look over here, we've got the scores of about 200 students, assuming that this is a sample from a given population of students. So we've extracted a sample of 200 students, and we've got the scores across read, write, math, science and social studies for all of the students here. The test is asking us to test whether the average score is 55 for all students, and then check for 50, then check for 52. Let's start off with one of the variables. We'll start with testing whether the average read score is 55 or not. So how do we test that? What is the average value of read in the sample itself? So I'm going to run a simple proc means procedure over here. Proc means data equal to class.hsb2. This is the library name oblique the dataset name, and I'm going to test it on the first variable that we need to test, which is read. So var read, run. I'm going to put in an ODS HTML so that it comes out in an easy to read manner, the output. And let's run it. So here we get the average of the read variable is 52.23, and the statement is asking us to test if the average score is 55 for all scores including read. So prima facie doesn't look like it is 55, but this is a sample. It does not imply that the population is 52, and we need to test whether that implies for the population or not. So coming back to our hypothesis testing procedure, right? I want you to create the null and the alternative hypothesis for this particular case. So what will be the null hypothesis? So as tested earlier, the null hypothesis is the starting claim that we make. So whatever we are claiming is assumed to be true. So what are we claiming? We are claiming that the average score of the population is 55. So let's go here and say that H naught, right? The H naught is that the population mean mu is 55. Then we are going to formulate the alternative hypothesis, or the HA. The HA is going to be the exact opposite of the null. The exact opposite is that the population mean is not 55, right? And now we have the sample mean as well. Sample mean, or X bar, is, let's test it on the tool. The sample mean is coming out to be 52.23. So the sample mean is 52.23, and of course we will have the standard deviation as well. Standard deviation is coming out to be 10.25. So this is the sample standard deviation. The sample standard deviation is 10.25. So can we extract the standard error of the mean? So as we mentioned, standard error, or the standard deviation of the sampling mean, is the sample standard deviation divided by under root of n, where n is the number of observations. So n in this case is 200. So the standard error becomes 10.25 divided by under root of 200. Now coming to the critical value method. So what are we exactly claiming? We are claiming that, assuming that this is the distribution, right? We are claiming that the population mean, make it a better figure, population mean is actually 55. Now if the population mean is 55, what does the central limit theorem tell us? The central limit theorem tells us that in a population with mean 55, irrespective of the distribution of this population, if I extract samples from this population, the mean of the samples will follow a normal distribution around this. Right? So I will get a normal distribution which looks something like this. Let me center it around over here. So if this is 55, let's get a straight line actually. I'm going to put it over here. Yeah, that's straight enough. This is 55, right? So I will get a distribution around the mean. So it will follow a normal distribution on both sides. So normal distribution, sorry, around 55. And since a normal distribution is symmetric around the mean, the area on this side is equal to the area on this side, which is 50% each. Now we've gone ahead and extracted a sample of mean 52. So our sample lies somewhere over here, 52.3. Right? Now we know for a fact that if we extract samples from population of 55, the sample means will follow a normal distribution around it, and the standard deviation of this normal distribution is the standard error of the mean. So this standard error is the normal is the standard sorry this standard error is the standard deviation of this sampling mean. This is not the standard deviation of the sample. So this particular normal distribution is the distribution of the sample means which I would have extracted from this population. Now I have got a sample of 52.3, right? Now in 95% of the cases, the sample that I extract from this particular population will lie within how many standard deviations of the population mean? Right, so if we've covered the properties of a normal distribution, we know that 1.96 standard deviations around the mean is going to give us the 95% confidence interval, right? So what is the standard deviation here? This is the standard error. So 1.96 standard errors around the mean will give us the 95% confidence interval. So if I say this, assuming we've got the standard error here, I extract the 1.96 standard error upper confidence limit, and then the 1.96 standard error lower confidence limit. What this will tell me is 95% of the samples that I extract from this population will lie within this region or within this upper and lower bound, right? In case my sample lies within this region, right, then I can go ahead and say, you know what, with the extraction of this sample, right, I'm unable to disprove the null hypothesis, right? Or if this sample lies outside this region, then I can say, that I'm able to reject the null hypothesis and go with the alternative hypothesis. And if I want to test it at 99%, then instead of 1.96, I'll go even further. I'll go up to 2.57 on both sides. So in this particular case, we'll go 1.96 on both sides, right? So how do I figure out whether this is within 1.96 standard errors or not? Right? I know what is the standard error. I calculate the standard error. I calculate the difference between these two and divide it by the standard error. So what I can do essentially is I can do 55 minus 52.3 divided by the standard error. Take the mod of this number. If this mod of this number is less than 1.96, which is the critical value at 95% level, then I will say that the null hypothesis is true, or I am unable to disprove the null hypothesis. In case this value is actually greater than 1.96, then I will go ahead and reject the null hypothesis and go with the alternative hypothesis and say that within the 95% confidence interval of the hypothesized population mean, we are unlikely to get such a sample. Therefore, I am rejecting the null and going with the alternative hypothesis. So this is the critical value method that we are going to apply, and I'm going to do it firstly using SAS. So I'm going to use SAS to calculate the value of this figure, x minus mu by sigma, or the standard error. So if I look at the presentation, the z or the t value, here we are. So the z or the t value is calculated as x bar minus mu divided by the standard error, where x bar is the population mean and mu naught is the hypothesized, x bar is the sample mean and mu naught is the hypothesized population mean. So this is the z or the oblique the t value. I'm going to do it on SAS. So the procedure on doing it for SAS is proc t-test, data equal to dataset name, formulate the h naught, right? Specify which variable you want to run it on. So let's do it over here. Proc t-test data equal to class dot hsb2. The h naught is that the value is 55, the variable that we want to do it on is read. Run. Let me include ODS HTML as well here. And that's it. Let's run this procedure and see the result. Go to results viewer, and here we have it. The t value is minus 3.82. Now minus 3.82 is greater, so the t value which I am getting, let me clear it off. Yeah, so let's run it again. So let me draw the axis. So this was the value of 55. Right? This was the distribution which I was expecting around it. Right? This is where 52.3 lies. And this distance between 52.3 and the null hypothesis is 3.82 standard errors. This is 3.82 standard errors, whereas the critical value at 95% level lies at 1.96. Therefore, this value is outside the acceptance region. The acceptance region is 1.96 standard errors on each side, which is the shaded region right over here. This value lies outside the shaded region. It lies in the rejection region. Anything which lies within the shaded region or within 1.96 standard errors on both sides of the mean, that is known as the acceptance region. Why do we call it the acceptance region? Because in this case, H0 is to be accepted. If it lies outside the shaded region, which is outside within 1.96 standard errors, which is this area over here and this area over here, this is known as the rejection region. Pardon my handwriting. So this is the rejection region. Therefore, if the sample lies in the rejection region, we are going to reject the H0 and we're going to say the alternative is accepted. And the alternative was that the population mean is not 55. Therefore, for the variable read, we've gone ahead and rejected this particular hypothesis. We're going with the alternative hypothesis. The population mean is not 55, i.e. we've got a sample with mean 52, right? And this sample comes from a population which does not have a mean of 55. It is something else. It is not 55, and we are doing it at the 95% interval. We're testing the t-value at 95% level. Right? Now let's go ahead and test the other variables as well. So I want to test now the next variable, which is right. So how can I do that? I can just go here, copy the same code, go down, H0, and same thing, I just replace the variable name with right, and I run it. And there we have it. The t value for variable right is minus 3.32. This is again greater than the mod of 1.96. Sorry, the mod of t value is greater than 1.96. And therefore I'm going to reject this particular hypothesis. What is the other tables of the t-test mean? So the first row that we have, the first table, simply the mean. So we've got the mean, we've got the standard deviation. It also calculates the standard error, which is the standard deviation divided by under root of n. Right? Then we get the minimum and the maximum value of the variable read itself. So the minimum value in the data set, the maximum value of the data set. Here we have again got the mean, and we've got the 95% confidence interval of the mean. So 95% confidence interval of the mean is simply mean plus minus 1.96 standard errors. Right? A sample or the population mean in 95% of the cases will lie between 51 and 54. We claim that we are testing 55 lies outside of this. And this is the standard deviation. Here we've got something which is known as the confidence interval, the standard deviation as well. So this is outside of our scope. We have not covered how do we calculate the standard deviation of the standard deviation or the standard error of the standard deviation. But this is also calculated using the CLT. We can ignore these two values for now. Here we've got the t value, and we've got something known as df, which is the degrees of freedom, and the p value, which we will cover in our next lecture. Right now we are going to only cover the t value or the critical value that we have to compare this t value against. And how is this t value calculated? This t value is nothing but x bar minus mu naught divided by the standard error. So x bar over here is this case is the sample mean, which was 52.7, divided by the hypothesized mean, which is 55, divided by the standard error, which is 0.67. So this is coming out to be minus 3.32. The mod of minus 3.32 is greater than 1.96. Therefore, this lies in the rejection region. So this hypothesis is rejected. Let's continue testing this for all scores, the other remaining scores. So we have got, we've done read and write, we've got math, science and social studies also pending. So in the code, instead of running it, one at a time, I can actually run the test for all the variables for an H0. If the H0 is same in one go, I simply enumerate the variables one after the other in var. So var v1, v2, v3, v4, v5 and so on. So we've got read, write, math, science and social studies. So let me type it in: math, science and SOCST, which is the spelling for social studies here, and that's it. And I run it and I'll get the result one after the other. So you've got it for read, t value is greater than 1.96, the null is rejected. For write, t value is again greater than 1.96, null is rejected. For math, t value is again greater than mod of t value is greater than 1.96, null is rejected. Again for science, null is rejected. For social studies, null is rejected. Right? We are disproving or we are rejecting the null hypothesis for all the variables. The average score is 55 for all scores. This hypothesis is rejected for all the scores. Next we want to test is average score is 50 for all scores. How do I do that? I simply take this code and change the H0. Let me change the H0 to simply 50. And now let's run it. Let's look at it. Variable read, right? T value 3.08. We are even rejecting it for at 50. The population is not 50 for read. We have rejected it. For write, T value is again an extreme value. We are rejecting it. We are rejecting it for math as well. For science, it's coming close 2.64, but close but no cigar. It's rejected for science as well. For social studies also we are rejecting. So even for 50 we have rejected. Test whether the population mean can be 52. Let's try this. Maybe third time lucky. 52. Let's see. For 52, t value is 0.32. What does this imply? Let's draw it out again. For read, I'm getting 52. Let's see. So here we have the axis and we have the distribution. Sorry. We are testing it at 52. The mean that we've got is for read is 52.23, which lies somewhere over here, right? Testing this distance between the mu naught and the x bar, right? This distance mu naught minus x bar in terms of standard errors, this value is coming within 1.96 standard errors. So 1.96 here, 1.96 here, this was the acceptance region. The mean of the sample is coming within the acceptance region. Therefore, the H0, that the population mean is 52, cannot be rejected. We cannot disprove this claim. Therefore, this claim still stands. Now, as you recall, in our previous lecture, I said null can never be proven. It can only be disproven. Only be disproven. Therefore, because the null stands does not mean that the population mean is proven to be 52. All it says is the sample that we've extracted, right? The sample that we've extracted, which had mean 52.3, is insufficient to disprove this claim, i.e. this claim still stands. Just because the claim stands does not mean it's true. We can never prove that the population mean is 52 unless we go ahead and measure the whole population, right? And that is out of that's not feasible. We are always working with samples. Therefore, using this sample, we've proven, or we've actually gone ahead and done a significance test, and the significance test has failed to disprove the null. Therefore, the population mean could actually be 52. We are not sure, right? We can never be sure, but what we do know for a fact is that the sample that we've extracted has failed to disprove the hypothesis, i.e. the hypothesis still stands, right? That does not mean the population mean is 52. Let's look at the other results. For read, acceptance region, right? Again, acceptance 1.16 is still less than 1.96. Math also accepted. Science also accepted. Even though it's negative, the mod of this value is within. So all it means is that instead of on the right hand side of the distribution, the sample is on the left hand side of the hypothesized distribution. Social studies, again accepted. Therefore, when I'm testing for the average score is 52 for all scores, right? This hypothesis is standing for all the scores at 95% level. Now, this was how we do it in SAS, and I'm now going to show how to do a single sample t-test on SPSS. The same procedure, I'm going to test the critical values against the same variables using SPSS. Carrying on and doing this on SPSS. So I've got SPSS open. First I'll import the dataset. It's a CSV dataset. So just select star.star. And go to the dataset, which is B2. Next, variables are on top of the row. It's a delimited file. Each line represents a case. It's comma separated. Okay, next and finish. So there we have the file. I want to run a single sample t-test on all of these variables. The way to do that, go to analyze. These are the various options that we have. We have an option called compare means over here. In compare means, very simply and elegantly put, one sample t-test. What is the variable that we want to test? I want to test the variable read. What is the value that we want to test? So we want to test the first value, which is 55. So I type in 55 over here. Let's see what are the options over here. So this is the confidence interval. I want to test it at 95% level. What is the missing value treatment that we want to do? So we want to leave it as the default exclude case analysis by analysis. And that's it. Press OK. And we get the t-test. So we will get a similar output as we get in SAS. So we get the means table. Read mean is 52.23. Standard deviation 10.235, 10.253 standard error, and then we get the t-value over here. So if I test the value over here that I got with this value, we will get the same, h naught equal to 55. So we got a value t-value of 3.82 for read, and here also we get a value of 3.82. So it goes up to 3.821 because that's 3 digits. Otherwise it's the same. We get the same standard error 0.725, 0.725, mean, standard deviation, nothing will change. Nothing can change, in fact. The formula is the same. And we get a t-value of minus 3.82, which is in the rejection region because it's greater than 1.96 at the 95% criteria. Okay, so let's try it for the other variables. So I go to, again, compare means, one sample t-test. Instead of read, just read. What happens if I select all the variables in one shot? So let's select all the variables in one shot. I see social sciences is classified as a categoric variable. So I'll just go to the data set, variable view, social sciences, change it from nominal to scale. That's it. So once I've changed it, I'll go back to the compare means. Yeah, it's all in a scale format. Test value 55, same options. Press OK. And there we have it. Very elegantly in one table, I get all the t values in one shot. They will be the same as I got in SAS. All of them are greater than the critical value, and all of them get rejected. What was the second problem? Test whether average score is 50 and then test whether average score is 52. Very simple. Go to analyze, compare means, one sample t-test, change from 55 to 50, press OK. All of them get rejected again. Right? So this first result was only for read. The second result was for all the variables at 55. Third result, all the variables at 50. And then I'm going to do is compare means, one sample, testing it at 52. Press OK. And there we get it. All t values are within 1.96 standard errors, or the mod of the t is less than 1.96. All of them, or this how the hypothesis for all the variables lies within the acceptance region. And that was how we did it on SPSS. So if you go to SPSS and compare means, you will see one sample t-test, then independent samples, paired samples, and ANOVA. So not to worry, I will cover all of these options and what do we mean by independent and paired sample t-test in the next few lectures. In this lecture, we're going to concentrate on one sample t-test for now. So this was conducting a t-test on SPSS. We've covered SAS. I'll move on to Statistica. First things first, import the dataset. Similar way, let's select where is all files. Yeah, there is all files. Navigate to the folder. Sorry, it's not all files. There it is, all files. HSP. Sorry, yeah. HSB dataset. Import selected sheet HSB2. Yeah, it doesn't matter whether I import from the CSV file or Excel file. So if you see over here, I've made a mistake. I have imported the top row as part of the dataset itself, and that's not done. So I'm going to import it again. HSB2. Get case names from the first row, or get variable names from the first row. That's the option I should have selected. Now I see variable names have gone over here, and that's what I wanted. Now let's go and test. How do I do a one sample t-test over here? Go to statistics and let's look at is the option gone? Let's check basic statistics. There we have t-test single sample. Press OK. What is the variable I want to test it on? I want to test it on read first. Okay, and so already test all means against the H0, so I want to test it at 55. Right, and let's look at what are the other options that we have. Histograms, P, box and whiskers, we've all covered this already in the other lectures. And that's it. I don't want to do any other test. In fact, a box and whiskers plot also I don't need that. And press summary. And there we have it. Mean 52, standard deviation, number of observations, the standard error, the reference constant, that is the H0. H0 is 55. The t value that we are getting, minus 3.82, which is greater than the critical value, hence rejected. And that's how we do a t-test on Statistica as well. And similarly, if I want to select all variables in one shot, I can do that. I click on all the variables. You can either drag it or press Control and then click all the variables. Press OK. Test all means against 55. And there we have it. Very simple. Look at the t values. All of them are greater than 1.96. It all gets rejected. Similarly, I want to test it at 50. Press that. Click summary again. All of it gets rejected. So I get over here, you will see these tabs. These are all the different tests or different iterations which I've been running. I go over here, change it to 52. I'll get the fourth tab, and there it is, the fourth tab, and the t-value in this case is in the acceptance region for all the tests. So this was running a single sample t-test using the critical value method across all three tools. As a exercise, I want you to look at the car sales data set and test the following claims. Average mileage or the MPG. So let me pull up the car sales data set. I'll pull it up in Excel. So there we have the car sales data set. First claim is average mileage is 30. So we have the MPG column, right? You have to test whether the average mileage in the data set is 30 or not, assuming this is a sample from a population, of course. Average fuel capacity 17.5. So we have fuel capacity as a variable over here. Test whether average fuel capacity is 17.5 or not, and then check whether average horsepower is 200 or not. This is average horsepower 200 or not. I want you to do this test using the critical value method for all these three claims, and the critical value that we want to test it against is at 95% levels. At 95% level, the value of the critical the t value should be less than 1.96. The mod of the t value, doesn't matter whether it's positive or negative, the mod should be less than 1.96, i.e. the t value that you compute should be from minus 1.96 to plus 1.96. If it is outside this region, then this claim that you're testing lies in the rejection region.